Today we're taking a look at parent functions, and we're also going to introduce the greatest integer function. So a little bit of a review from Algebra 2 and then a little something new. So it is expected that you are familiar with the equations and the graphs of several parent functions. We're going to start off by just a little bit of a review here, writing the equation and sketching the graph of the parent function for each of the following. So the quadratic function has the equation y is equal to x squared. So that is your very basic parabola. So something like that, where you go over 1 and up 1, over 2 up 4, over 3 up 9. So whatever the input is, you square it. Okay? And we have the square root function. Y is equal to the square root of x. This has a domain of 0 to infinity. We start at 0, and then the graph looks something like that. So over 1 up 1, over 4 up 2, over 9 up 3, all the inputs you take the square root of to get the output. And we have the cubic function, y is equal to x cubed. So this is the cubing function. So it does go through the origin, and it has a little bit of a kind of a snake-like curve. Right at the origin, it gets flat, and that's important to note. So right at the origin, it does get flat. And then it goes, the domain is negative infinity to infinity. The range is also negative infinity to infinity. But it does get flat there at the origin, even flatter than what I show here, a little bit flatter than what I show there. Later on, we're going to have another function that is a little similar to this shape, except at the origin it does not get flat. It goes through the origin at a 45-degree angle. Okay, the absolute value function, y is equal to the absolute value of x. It has a V-shaped with the vertex right at the origin. Over 1 up 1, over 2 up 2, etc. The constant function. This is the function where y is equal to some constant. 2, 5, negative 7, negative 3 halves, any constant. I'm going to call it y is equal to c, and that graph is a horizontal line at wherever y is equal to c is. So that would be where y is equal to c on that axis. The reciprocal function, y is equal to 1 over x, the reciprocal of x. This one has some asymptotes right on the x and the y axis. So the range and the domain are everything except for 0. We have those asymptotes. And the reciprocal function has these little arms, do something like that. And this is the point 1, 1. This is the point negative 1, negative 1. So the reciprocal function lies in the first quadrant, and the third quadrant never touches either axis. The identity function is y is equal to x. It's like looking in a mirror. It's the exact same thing. And this is the line y is equal to x. It goes through the origin. Over 1 up 1, over 2 up 2, over 3 up 3. Whatever the input is the output. Alright, so those I want you to just know. Those you really do need to know. Okay, and we will get some more that you also need to know, like y is equal to e to the x, y is equal to log x, things like that. Alright, you might not be as familiar with this next function called the greatest integer function. So if you are a highlighting type of person, like me, you might want to highlight that. That's a new function for us. It's also known as a step function. It is not the only step function, but it is known as a step function. We'll look at why in a second. And the equation for that looks a little bit different. It has this equation. F of x is equal to this greatest integer of x. On your notes packet, this did not translate to our school printer. So I believe in your notes packet, you may be showing something like that. The bars here just didn't copy right. So go ahead and add the greatest integer bars, okay? If they're not already on your packet, go ahead and add those. It's like a bracket with a double bar, okay? The domain is the set of all real numbers, so we can put any value of x in there that we want. The domain, the real numbers are denoted with this R with a double bar there. The range, though, is not the real numbers. The range is only the set of integers. So the output is always going to be an integer. The symbol for integers is this Z with a little bar, double bar. FYI. You don't have to know that, but just a little FYI. You'll see that. Okay. All right, here's the definition for the greatest integer function. The greatest integer of x is the greatest or largest integer, which is less than or equal to x. It is sometimes helpful to think of a number line when you are determining values for the greatest integer function, okay? So I'm going to draw a number line. I'll draw a number line like right here. Okay, so here's 0, here's 1, 2, 3, 4, 5, 6, etc. Negative 1, negative 2, negative 3, negative 4, etc. Okay? All right. If you're looking for f of 3, when f is the greatest integer of x, this would be the greatest integer of 3, which is the largest integer less than or equal to 3. Since 3 is already an integer, this is just 3. Anytime you have a plain integer in there, the greatest integer function just spits it back out. F of 3.2, the greatest integer of 3.2. We go to 3.2. We want the largest integer less than or equal to that number. And the greatest integer less than or equal to 3.2 is 3. So if we're graphing these, if I were graphing y is equal to the greatest integer of x, f of 3 is 3, so over 3, up 3. F of 3.2 is also 3, so at 3.2 here, at 3.2 we're still up at 3. F of 2.9, that's the greatest integer of 2.9. And if I go to 2.9 on the number line, what is the largest integer less than or equal to 2.9? 2. So this would just be a 2. So everything between 3 and 4, but not including 4, would be up here at 3. But once we get to 4, it jumps up to 4. Okay? F of 0.1. Here's 0.1. The greatest integer less than or equal to 0.1 is 0. F of negative 0.2. Here's negative 0.2. The greatest integer less than or equal to negative 0.2 is negative 1. So you're always going to the left on the number line, unless you're already on the number itself. Okay? So what would f of negative 121.3 be? It would be the left one, which would be negative 122. So f of 0 is 0. F of 0.1 is also 0, all the way up to 1, not including 1 though. Once you get to 1, it jumps up to 1. And then it goes like this, and like this. And now you see why it's called a step function. We have these what look like little steps in a staircase. That should be open there. Oh, that should be open. That looks like little steps. So when I graphed this on Desmos, this is what it gave me. There's the greatest integer function. Okay? Step functions do make for interesting questions when we begin calculus, when we start what are called limits. So we will note that. And so I know that that's an odd little function, but yeah, it's a little bit weird, a little bit strange, but any new function when you first see it might seem to be a little strange. So this is just another one. Alrighty, number 3. Let's review translations of the graph of a function. If we want to shift a graph right h units, then we subtract h from each x in the function. So the new function will be f of x minus h. If we want to go to the left h units, then we will add h. So right you subtract, left you add. Our new function would be g of f of x plus h if we wanted to go left. Going up k units, we want to shift it up k units, we add k to the entire function, way back in the back. So g would be f plus k. Down k units, we subtract k. So you probably remember those. To flip the graph over the x-axis, it's a reflection over the x-axis. You take the negative of the entire function, okay, of the entire parent function. So g would be negative f of x. To reflect your graph over the y-axis, you put a negative in front of the x, okay. If there's a shift and a reflection, you put a negative in front of the shifted x, all right? And then there are also dilations, and dilations can definitely be more confusing. I'm going to need you to know the difference between a vertical dilation and a horizontal dilation, specifically a vertical stretch or compression and a horizontal stretch or compression. So what we're starting with is this graph that I just did on Desmos. It's x cubed minus 3x, and this is the graph of x cubed minus 3x. So in all of the next graphs that I show you, the solid graph is this parent graph. It's not really a parent function, but it's our starting function, okay? Let's examine some dilations of f. What would happen if we put a 2 in front of the entire function? A 2 in front of the entire function. We would be putting a 2 in front of the entire thing, so we would get that for our new function. When I graphed that on the same graph as our original f, I got this dashed line graph. So this is our translated graph. What did it do? What did it do? It didn't shift it, but what it did was dilate it. It doubled every y value, right? It doubled every y value. This y value was at 2 and now it's at 4, so it doubled it. We doubled the y value. And since f of x is y, it makes sense that we would be doubling the y value. This is a vertical dilation of factor 2. It stretches the graph vertically by a factor of 2. We're multiplying it by 2, okay? Let's take a look at this one. If you put a 1/2 in front of f, then you are multiplying 1/2 by your function, okay? And we get that for our function. When I graphed that, I got this dotted line. So what did that do? It was still a dilation, and it was still a vertical dilation, but this time it cut the y values in half. It compressed the y values, all right? So this is called a vertical dilation of factor 1/2, and that compresses the graph, the original graph, vertically by a factor of 2. It does not compress by a factor of 1/2. That would be saying, like, I lost -2 pounds, okay? That's like you're double doing it. It dilates it by a factor of 1/2, which means it compresses vertically by a factor of 2. Alrighty, let's do another one. What would the graph of, what if we put that 2 not in front of the entire function, but only in front of the x. What would that do? Well, it makes sense to me that if I put it in front of the x, it's going to affect the x's, right? It's going to affect the x's. So, yes, the new graph did this. Sorry. There we go. All right, the new graph did this. And that 2, what did that 2 do? The 2 in front of the x, it compressed it horizontally. It took the graph and just squeezed it in towards the origin, didn't it? Okay. This is a horizontal dilation, which of a factor of, this is a horizontal dilation. It's a horizontal dilation. It was a 2 in front of that x, right? That's a horizontal dilation, but it's of a factor of a half because everything is cut in half. It's of a factor of a half. Every x is cut in half. This x was 1. This x is a half. So it's a dilation of factor 1/2. That compresses the graph. That compresses the graph horizontally by a factor of 2. Okay? Again, you don't want to double. If you're using the term compresses, you don't want to say it compresses by a factor of a half, because then you're kind of double doing the meaning of that compression. Okay? All right. What if we have a half in front of x? Well, if we have a half in front of x, look what it did to the graph. It stretched it. It stretched it out horizontally. It pulled it away from the origin in a horizontal direction. The y here did not change. The x is what changed. Okay? So, and it doubled it, didn't it? The 1/2 did the opposite of what we thought it might do. Maybe. Maybe it did. Okay? So the 1/2 here is a horizontal, I should have highlighted that. The 1/2 in front of that x is a horizontal dilation of factor 2. It doubled it, right? So it's a factor 2. It stretches the graph horizontally by a factor of 2. Okay? So the horizontal is a little bit of a more confusing one, and I definitely understand that, all right? But it kind of makes sense because back when we were doing the right and the left, if we're moving right h units, we subtracted h. If we went to the left, we added h. It's almost backwards of what you think it should do, because left, away from the origin, is in the negative direction, true? But here we are adding it. So it's kind of opposite of what you think. Whereas the y, changing the y, it is exactly what we expect. Up is plus, down is minus. Okay? So horizontally, you want to think in the opposite of what you might expect it to do. Okay? So if I see a half here, that's a horizontal dilation of factor 2. If I see a 2 here, it's a horizontal dilation of factor 1/2. Okay? Alrighty. So yes, note that in all 4 of these dilations, there is a stretch or compression by a factor of 2, but the phrasing is different depending on whether it is referring to vertical or horizontal. Okay, let's go back to our original. It's still solid. The original is still solid. What if we want a vertical dilation? We want a vertical dilation of factor 2. So we want for our y to double. So I'm focusing on that point right there, that hump of our original, and it doubled, didn't it? It was at 2, and now it's 4. So it is a vertical dilation of factor 2. And we want a horizontal dilation of factor 3. So we want it to stretch horizontally by a factor of 3. So again, we're here at x is equal to -1, and here x is equal to -3. So it stretched it we multiplied by 3 to get there. Okay? What would the equation look like? Well, our new equation, I might call it G. They don't name it for me, so I'll just call it G since we started with F here. Okay, the vertical dilation of factor 2 is 2 times F. I know that. Vertical, it's 2 times the Y, so it's 2 times your F. Okay, the horizontal dilation of a factor of 3, though, we need a 1/3 to make a horizontal dilation of a factor of 3 in front of the X. And that's it. Okay. I'm not going to go ahead and make the actual equation with x's in it. I'm just going to leave it like that. Okay. All right, let's do another one. Consider this graph below, which is the graph of the same f. I'm still dealing with the same f in solid. That's the solid. And y is equal to g of x, which is a translation of the graph of f. Here's the translation. Okay, so question number 1 is does G have a horizontal or vertical shift? Is there a shift? No, there's not a shift. I'm looking kind of at the center of my original, which is at the origin, and that is still the center of my new graph. It's still the center of my new graph. So there's not a horizontal or vertical shift, not a shift. Is it a horizontal and or vertical dilation? Absolutely. I see a horizontal dilation and I see a vertical dilation because it went down. So yes, both. Oops. Yes, both. Okay? All right, now we're going to write the equation. So they call it G, so I'm going to call it G. Okay? All right, let's focus first on the vertical dilation. I started here when y was 2. And the corresponding point on the new translated graph is right here, right? So I started at 2, but now I'm at 1. What did I multiply 2 by to get 1? I multiplied by a half. So I'm going to need a 1/2 right there in front of my f. Okay? Now what did we do to the x's? What did we do to the x's? I was here when x was -1. Now I'm at x is -3. So what do you multiply -1 by to get -3? Well, you multiply by 3. So what do I need to put in front of the x? Not 3, because that would be a compression. That would be a compression. So we want 1/3 in front of the x for the horizontal. Okay? In class, when I taught this in class, I let you in your group do this one. Okay? So you might want to pause and try this on your own and then come back. All right. Is H a horizontal or vertical shift of f? Still this original f. Now we have this new function h. So what happened to get h? The middle of f was the origin, and the middle of h is still the origin. So no, there is no horizontal or vertical shift. Is there a horizontal or vertical dilation? For that, I look at my original little local max here, the little hump here. Did it move? Yes, it did. It went up and it went over because now it's right here. So yes, both. All right, let's write an equation for h. Let's handle the vertical dilation first. We started at y is 2, and now we're at y is 6. What do you multiply 2 by to get 6? You multiply by 3. So 3 times f. Okay, now what happened to x? We started when x was -1, and now it appears, and you kind of have to approximate that, but it appears like it's at 1/2, a -1/2. So what do you multiply -1/2 by to get -1/2? 1/2, right? So do I want to put a 1/2 here? No. It's in the x's. We're dealing with the x's, so we do the opposite. Instead of multiplying by a half, we're going to multiply by 2x. That's the equation for h there. Okay? All right. Let's review a little bit what we've talked about here. We've done a bit. Some review and some new, right? Let me focus that again. Focus that one more time. Okay, hopefully it'll be fine. All right. Let's write the equation of the square root parent function, square root, reflected across the x-axis. So when I see that, I know I'm going to need a negative in front of my f. Okay? I know I'm going to need a negative in front of my f. Shifted to the right 4. When I see that, right 4, I need an x minus 4 inside with the x's. Down 3, that means minus 3 way outside my entire function. With a vertical dilation of factor 6. Vertical dilation means I need a 6 in front of my f. Okay, let's put that all together. I knew it was going to do that. Let me try to, gosh darn it. Let me try to do this again. It's not, oh, okay, there we go. It autofocused. Okay, all right. So let's write the equation. I'm just going to call it y. Y is equal to, oh, come on. I hate it when it does that. Okay. Golly Moses. Okay. Y is equal to, all right, let's see. I'm going to start with the vertical part. So reflected across the x-axis has a minus in front, and we have a 6 in front, so I need a negative 6 in front. Yeah? And then, is there a horizontal dilation? No, but I do have that shift, so x minus 4. And then lastly, everything is minus 3. Okay, let's write in the equation of the quadratic parent function, still reflected across the x-axis. That'll make it a negative f of x. Shifted to the right 4 still, so still x minus 4. Down 3 still, so the whole thing minus 3. Horizontal dilation of factor 6. Horizontal dilation of factor 6. So that's going to be a negative in there with the x's. Okay, a negative in there with the x's. So it's going to be f of negative something. I'm sorry. Oh gosh, not negative, 6. Oh gosh, still not 6. Horizontal dilation of factor 6 will be a 1/6 in there with the x's. Goodness gracious. Okay. Alrighty, let's put it all together. Okay, first this reflection. That's the negative is the only thing that's out in front of the whole thing, right? Negative. All right, it's the quadratic parent function. Come on, it's the quadratic parent function, and okay, it's a quadratic parent function, and we're shifting it to the right 4 with a vertical dilation of factor 6, which makes us put the 1/6 in there. So it's going to be 1/6 times x minus 4. You apply the 1/6 to the shift. That's all in there in our parent function, so that all is being squared. And vary at the end, minus 3. Down 3. Okay, let's do one more. Write an equation for the absolute value parent function. Shifted right 4, up 3, vertical dilation of factor 5, horizontal dilation of factor 3. Horizontal dilation of factor 3. Remember, you're going to need a 1/3 in there with your x's. Vertical dilation of factor 5, you just put a 5 way outside in front of the entire parent function. Okay, it's the absolute value parent function, right 4, up 3, so we have a shift inside. Okay, well, we have a shift inside and we have a up plus 3 way outside. So y is equal to, okay, vertical dilation of factor 5, so 5 way outside, no flip. No reflection in the x or y axis. Okay, so now I'm going to start my absolute value. Okay, horizontal dilation of factor 3, so 1/3, right 4, so x minus 4, up 3, close your absolute values, up 3, up 3. Did I get everything? Absolute value, right 4, up 3, vertical dilation factor 5, horizontal dilation factor 3. Yes, got everything. Okay, let's write an equation for each of these graphs. Okay, alrighty. Well, this is a parabola. Okay, the parabola usually starts here and goes over 1, up 1, over 2, up 4, over 3, up 9. It usually does that. Oops. In both directions. Okay, usually does that. So clearly it flipped it, right? So I'm going to need a negative out in front of the quadratic. Yeah? All right. Is there a shift? Yes, there is a shift because this guy right here has definitely moved. It moved 1, 2, 3, 4 to the left, and it moved up 3. Left 4, up 3. Okay. Is it dilated? Is it skinnier or fatter than it was before? No, it was not. It's not any skinnier or fatter. I see over 1, down 1, over 2, down 4, over 3, down 9. It's not any dilated. There's no dilation. So y is equal to, y is equal to, negative because we did flip. Okay. X plus 4, right, squared plus 3. The up 3 goes at the very end. Okay. All right. Here we have the greatest integer function. And the greatest integer function normally starts right at the origin and has that first little leg right there, and it ends right. The first step starts there. So how can we write an equation to get this one? Well, what I see is no dilation. There's no dilation because everything is the same length that it was when we started. So there's no dilation. But there definitely is a shift. And we can think of lots of shifts to get from here to one of those things, right? We can think of lots. I could just shift it up 3 units. So one equation would be our greatest integer function plus 3. Or I could take this and shift it to the left 3 units. That equation would be the greatest integer function with an inside the greatest integer with the x's plus 3 because we're going left 3. Or I could go up 4 and right 1. That would be x minus 1 inside and then up 4. All of these would give us that graph. So this time with the greatest integer function, there are lots of equations that would be correct. For the one we just did though, there is one and only one equation that would make that graph in rectangular form. In other forms there might be more. Okay. Let us now graph a couple. How do we graph this? So here I see here a shift. So I see that our parent function is the parabola, but the vertex, I'm going to shift the vertex first. The vertex of the parabola I'm going to shift first. I'm going to go to the left 2 and up 3 to shift that vertex. Left 2, up 3. There's my new vertex. Now the next thing I notice is that there's a negative. So instead of going up, we're going to go down. And then I see this 1/2. Normally we go over 1, down 1. But with that 1/2, we multiply that by 1/2. So instead of going down 1, we only go down 1/2. Normally we go over 2 down 2, over 2 down 4, normally. But since we are multiplying it by a half, we go over 2 down 2. On both sides here. I'm going to go ahead and do that too. Okay, normally we go over 3 down 9. Now we're going to go over 3 down half of 9, 4 and a half. So 1, 2, 3, 4 and a half on both sides. Normally we go over 4 down 16. Now we're going to go over 4, 1, 2, 3, 4, and down 8, half of 16. 1, 2, 3, 4, 5, 6, 7, 8 on both sides. And that is plenty to get a very nice, accurate graph of that equation. Pretend that that's smoother over here. It kind of got wonky. Okay, one more. All right, we're starting with our reciprocal function. That's the one, the reciprocal function is the one with the asymptotes on the axes, right? And it does this. Yeah? Well, that, kind of. All right. So when you see a shift, in which we definitely see a shift here, I'm going to shift the center of my asymptote. So I'm kind of shifting my origin here. Okay? All right. Where do we want to shift? We want to shift right 3 and down 2. Right 3, down 2. So right 3, down 2. That is my new origin. That's my new origin. I don't want to use my purple. It looks black on here, but it's actually purple on the page. I don't want to draw the asymptotes in purple because that's really not the graph. It helps form the graph. So I'm going to put my new asymptotes in a different color, this light lime green. Okay, and now I have my new axes. There is no dilation here, but there is a flip. There's no dilation, that's still just a 1 there, and there's nothing being multiplied by the x down here, so there's no dilation going on. Okay, but there is this flip. So what's that going to do? It's going to flip it over the x-axis. So this leg is going to be down here in the 4th quadrant. This leg is going to be up here in the 2nd quadrant. And how close does it get to the asymptotes? It gets exactly like 1 unit away in both directions. So it gets this close without a dilation. Without a dilation, it gets that close on both sides. Okay, so I'm just going to have that point on there, and then I'm going to sketch out my little arms of this reciprocal function like that. Okay, and that is our talk on parent functions, and a little bit of something that we reviewed, a lot of review and a little something new. All right.